This Zoom session is being brought to you by the fractal snow ring. One of my favorites. All right, here we go. For today, we skipped part 2 as an extra credit set. It's going to be, let's see, how does that go? Polar equations and graphs. We'll get to it later if you wish, but it's extra credit. This is a set, however. Complex arithmetic and trigonometry and de Moivre's theorem. Turns out the complex arithmetic is an arithmetic of rotations, and that's why, and trigonometry is intimately involved, and we'll see why in a moment. Okay, we start with a complex plane denoted by a Greek fraktur letter C, German fraktur letter C for complex. It contains the real line, is 0, 1, -1, 2, -2, and so on, back and forth. It also includes complex quantities, I, the square root of -1, minus the square root of -1, over 1 and up, I is 1 plus I, and so on and so forth. Complex numbers are the form A plus IB. A is the real part, B is the imaginary part. It's over A units and up B units, like that. This I is the square root of -1. Its equation, defining equation, and its square equals -1. Now, that's what the complex numbers are geometrically. Basically, the 2 dimensions. It's ordered pairs, but it also is an arithmetic. So we need to find plus, minus, times, and divide on it. So here we go. Plus is easy. We combine like terms. A plus IB plus C plus ID is A plus C plus I times B plus D. We'll just use distribution on it and like terms on it, just like it was ordinary, like it was real numbers. And yeah, so. So the real and imaginary parts add separately and subtract separately too. Now, complex multiplication is a little more complicated. We can use what might be called FOIL, and I squared equals -1. So A plus ID times C plus ID. First is AC. Outer is A times ID. Inner is I times BC. And last is IB times ID, and I squared equals -1, so it's minus BD. Next step is to combine the real numbers and the imaginary numbers. So you get AC minus BD is the real part, plus I times AD plus BC is the imaginary part. Okay. However, we're going to rewrite this in terms of polar forms, polar coordinates. So imagine the complex number Z equals A plus ID. It's over A and up B. But we want to know what distance R is it out from the 0, and what angle theta is it from the positive real axis. Well, okay. Like with polar forms last time, A equals R cos theta and B equals R sine theta. That's just basic right angle trigonometry. And since Z equals A plus IB, then Z equals R cos theta plus IR sine theta, and lo and behold, a common factor of R factors out. Z equals R times cos theta plus I sine theta. Now, the nice part about this is that this is a product of 2 parts. And this part is all real numbers, just R. And this is all, it's all about R only. And this part is all its own thing, is all about theta only. So we've separated R and theta in this notation. Now, R is the radius. That's easy enough to find. It's root of A squared plus B squared. And theta is the angle from the positive real axis. And you can find it as arctan B over A or pi plus arctan B over A, depending upon if A is positive or not. Okay, now this deserves a name, cos theta plus I sine theta. Now it has a somewhat obsolete name, but you see it still here and there. Cis theta, cosine plus I sine. Cis, it has nothing to do with sexual politics or identities or whatever. I don't want to talk about that. This got here first. We math nerds got here first. This is what cis originally means. Cosine plus I sine theta. It is located, cis theta is located on a unit circle in the complex plane at a distance 1, so that's the unit circle, at an angle theta. So, this is theta. So, Z equals A plus IB is the rectangular form over A up B. R equals R cis theta is the R cis theta is the polar form. Out R at an angle theta, like it's polar coordinates, like as I said the other day, like an air traffic controller's view of the world. Now here's the thing. It turns out that rectangular form makes adding and subtracting complex numbers easy enough. We just do it by terms. A plus IB plus C plus ID is A plus C plus I times B plus D. Well, it turns out that polar form makes multiplication easy. R cis theta times S cis phi, R times S, but wait a minute, we then have cis alpha times cis beta. What is it? Okay, well, it will involve only alpha and beta. So, well, let's see how exactly. All right, here, cos alpha plus I sine alpha times cos beta plus I sine beta. All right, now after a bunch of complex arithmetic, which I won't bother going over, it's fairly easy. We cos alpha cos beta here minus sine alpha sine beta minus because we have an I squared. And then I sine alpha cos beta here, I cos alpha sine beta here. So this is the imaginary part. Now here's the thing. Cosine cosine minus sine sine and sine cosine plus cosine sine, these should be familiar to you. We saw them earlier in the angle addition formulas for cosine and sine. Cosine alpha cos beta minus sine alpha sine beta is in fact cosine of alpha plus beta. That's the angle addition law for cosines. Sine alpha cos beta plus cos alpha sine beta is sine of alpha plus beta. That is the angle addition formula for sines. So he gets cos of some plus I times sine of some, but cosine plus I sine is cis. So this is cis of alpha plus beta. So cis alpha times cis beta equals cis of alpha plus beta. Cis turns addition inside to multiplication outside. It's rather like an exponential. A to the x plus y is a to the x times a to the y. This is very similar, and there is a sense in which cis is in fact an exponential. Now, okay, if cis turns addition into multiplication, it'll turn subtraction into division. This just follows from this. And n times alpha, which is alpha plus alpha n times into cis alpha times cis alpha times cis alpha n times, in other words, an nth power. So cis of n alpha is cis alpha to the nth. Or wording it the other way around, cis product of cis is a cis of a sum, ratio of cis is a cis of a difference, power of a cis is cis of a multiple. Now, if you have two complex numbers written in polar form and you multiply them, R cis alpha times S cis beta, well, okay, you have RS that multiplies, and cis alpha times cis beta is cis of the sum. So RS cis of alpha plus beta. Similarly, if you divide them, then the R cis alpha over S cis beta, well, the length, the radius is R over S, and cis alpha over cis beta is cis of the difference. So when you divide complex numbers, you take the ratio of their magnitudes times cis of the difference of their angles. And finally, an nth power, well, from here, we get the r to the n, we take the nth power of the radius times cis of n alpha, n times the angle. So here, if we have r is cis, if you have z is r cis alpha and w is s cis beta, then the product ZW will be the length RS and the angle alpha plus beta. Complex multiplication multiplies lengths and adds angles. Now we're going to do a trickier thing, and that is finding roots of a complex number. To solve W to the n equals R cis alpha. Find W. Okay, well, here's what we're going to do. Let's W be denoted by S cis beta, and we'll find out what S and beta are. So substituting this into this, we get S cis beta to the nth equals R cis alpha. All right, because nth powers, just take the nth power of the radius and n times the angle. We'll get S to the n cis of n times beta equals R cis beta. Now, I didn't say sufficiently, but if you have two numbers with the same, if you have a two polar coordinate versions of the same complex number, then the radii must be the same. In this case, s to the n equals r. And the angles differ by an integer multiple of a rotation, because you go once around the circle, you want it where you were. So n beta has to be alpha plus an integer multiple of a rotation. So since s to the n equals r, s equals nth root of r, we have s. And n beta equals alpha plus 2 pi k for k some whole number. And to solve for beta, we divide by n, and beta is alpha plus 2 pi k over n for k some whole number. So we get the nth root of r cis theta, r cis alpha, namely nth root of r, you take the nth root of the radius, cis of alpha plus 2 pi k over n. You take 1/nth of alpha plus some integer multiple of a rotation. And k, the integer multiple of rotation can be anywhere from 0 up to n minus 1. There'll be n separate roots, all spaced evenly around a circle. Now we can rephrase all this. Cis theta, I said that it resembles a complex, an exponential. In fact, if we get into in the calculus later on, we will see that cis theta is the same as e to the I times theta. So in other words, okay, this involves giving a definition of a complex power of e. Well, okay, there are some formulas, and you plug in theta, and out comes cos theta plus I sine theta. So this acts like an exponential because in a way it is. So the preceding results. If you multiply two powers of e to the I alpha times e to the I beta, it'd be e to I times alpha plus beta. You add the angles. If you divide, you subtract the angles. You take an nth power, you take an n times the angle, and so on. Take an nth root, you take 1 over nth times the angle plus a multiple of a rotation. So let's start from some examples. Here's 4 minus 4i. We'll find its polar form. Well, it's over 4 and it's down 4 like this. Here's an angle theta, here's a distance r. Well, okay, it's easy enough to find. This r is the hypotenuse of an isosceles right triangle with side 4. So its length is root of 4 squared plus negative 4 squared. It's 4 root 2, easy enough. And this is an isosceles right triangle, so this is a negative 45 degrees. Negative because it's a clockwise turn. So 4 minus 4i is r, 4 root 2, cis of angle, negative 45 degrees. 2 cis theta. Sorry, 2 cis 120 degrees. What's that? Well, okay. Cis of 120 degrees. You go around 120 degrees. That remains 60 here. So it's going to be a 1 by 2 by root 3 triangle. This would be minus 1. So cosine of 60 is minus a half. This is root 3 over this 2 is cosine is root 3 over 2. Sine is root 3 over 2. So 2 times minus a half times I root 3 over 2. Multiply the throw out by the 2, you get minus 1 plus I root 3. Here we have two complex numbers, 2 cis 40 and 4 cis 20. And let's find their product and their ratio in polar form. For their product, we multiply their lengths, 2 times 4. Cis of, we will add their angles, 40 plus 20. 8, 6, 60 degrees, and then we're done. We can go a little further, but that's not strictly necessary. Z over W, we take the ratio of their lengths, 2 over 4 here. Cis of difference of their angles, 40 minus 20 here. You get 1/2 cis 20 degrees. So there these are. All right. Here we have two numbers, 2 plus 2i, root 3 minus I, find their product and their ratio in polar form. All right, Z over 2 up 2. So isosceles right triangle. The hypotenuse is root 2 times the side, so it's 2 root 2. The angle is 45 degrees, so 2 root 2 cis 45. For W, it's over root 3 down 1. It's easy enough to check that this third side is 2 by Pythagoras. This angle is minus 30 degrees. It's a 30, 60, 90 triangle. And so we read off W equals 2, the hypotenuse, cis of negative 30 degrees, the angle. So 2 root 2 cis 45, 2 cis negative 30. Okay, their product, well, you can multiply the lengths. 2 root 2 times 2 is 4 root 2. Cis of, add the angles, 45 minus 30 is 15. 4 root 2 cis 15 degrees. Their ratio, we take the ratio of their lengths. 2 root 2 over 2 is root 2. We take the difference of their angles. 45 minus negative 30 degrees is 45 plus 30 is 75 degrees. So the ratio is root 2 cis 75 degrees. Now here we're going to find some powers. 4 cis 40 degrees to the third power. Here, let's find the rectangular form. Okay, a third power, you take a third power of the length, 4 cubed. We take a 3 times the angle, 3 times 40. So it's 4 to the third cis 3 times 40. 4 to the third is 64. 3 times 40 is 120 degrees. 64, cis 120 degrees. Now we already saw earlier, cis 120, cosine is negative a half, sine is root 3 over 2. So cis 120 degrees is minus a half, we'll side root 3 over 2. That times 64, you multiply throughout, a factor of 2 cancels. We get negative 32 plus I 32 root 3. And there we are. You have a fourth power of root 5 cis 3 pi over 16. So, okay, fourth power of root 5 is root 5 to the fourth. Fourth power of cis 3 pi over 16 is cis of 4 times 3 pi over 16. Okay, square root is a half power to a fourth power gives you a 4 halves power of 5. 4 times 3 pi over 16 is 3 pi over 4. So 5 to the 4 halves is 3 pi over 4. 5 to the 4 halves is 5 squared, or 25. Cis 3 pi over 4 is in the second quadrant. Minus root 2 over 2 is the cosine. Root 2 over 2 is the sine. And then multiply all that by 25, you get negative 25 root 2 over 2 plus I times 25 root 2 over 2. That's the answer here. Here we have a difference, 1 minus I to a fifth power. 1 minus I is over 1, down 1. There's this, the radius is root 2. This angle is negative 45 degrees. So this equals root 2 cis negative 45 degrees, all to a fifth power. Okay, so we take the length, root 2, to a fifth power. Cis of 5 times the angle, 5 times negative 45 degrees. Root 2 to the fifth, that's 2 to the half to the fifth, or 2 to the 5 halves. 5 times negative 45 is negative 225. All right, 5 halves is 2.5. So you write it as 2 to the second times 2 to the half. Negative 225, well, we add 360 degrees because one full rotation leaves the thing where it is. And you get 135 degrees. And that's in the fourth quadrant, is it? No, it's the second quadrant. Is that right? Yes, it's in the second quadrant. You can easy enough to check that the cosine of 135 is a minus root 2 over 2. Sine is root 2 over 2. This will be 4 root 2. After some multiplying and this and that, root 2 squareds canceling and so on, you get minus 4 plus I times 4 is this fifth power. Now, we're going to be solving a root. Find the fourth root of 4 minus I 4 root 3. So you want to solve w to the fourth is 4 minus I 4 root 3. Now going over 4 and down 4 root 3 gives you, by Pythagoras, gives you a radius of 8. And this is a 30, 60, 90 triangle. So this angle, this clockwise angle is negative 60 degrees. So w to the fourth equals 8 cis negative 60 degrees. Now the formula goes, so therefore w will take a fourth root of this length, 8. Okay. And we'll have 1/4 of negative 60 plus some integer multiple of a rotation. So 8 to the 1/4 cis negative 60 plus 360k over 4. All right, let's simplify a little bit. 8 is 2 cubed. The 1/4 is 8 to the 3/4 power. Cis of, okay, negative 60 over 4 is negative 15 degrees. 360k over 4 is 90. Okay, so 2 to the 3/4 consists of negative 15 degrees plus 90 K degrees. So, okay, so these are all on these 4 values. Solutions are all on the circle radius 2 to the 3/4. Here, one is located at negative 15 degrees. Add 90 degrees to that, you get, this is the one at 75 degrees. Here's, we'll add 90 to that, get one here at 165 degrees. Add 90 to that and get one at 255 degrees, and another 90 degrees gets you back here.
How did you get the 2 to 3/4?
How do I get 2 to the 3/4 and 8 to the 1/4?
Yeah.
8 is 2 to the 3rd.
Oh, okay.
So 2 to the 3rd to the 1/4, you multiply the exponents 2 to the 3/4. Okay? Good. Now let's find the complex fifth roots of I. W to the 5th equals I. Well, I is cis 90 degrees times 1. So, okay, a fifth root, we'll have a fifth root of 1, which will be 1. Cis of, here we have 90 plus an integer multiple of pi, an integer multiple of a rotation, excuse me, 2 pi radians. And I'll divide it by 5. Okay, great. 1/5 of 90 is 18. 1/5 of 360 is 72. Fifth root of 1 is 1. So 1 cis 18 degrees plus 72 K degrees. All right, so these are all on the unit circle on account of this 1. There's one at 18 degrees, add 72 degrees, get one at 90 degrees. In other words, I again, I to the 5th equals I. And one at 62 degrees, one at 234 degrees, and one at 3 to 6 degrees. 5 on a regular pentagon, fifth roots. In general, a nth root of a complex number, they'll be located, n of them, in a regular n-gon in the plane. Okay, that does that.